So yeah, good morning. Welcome back to the Galileo Masterclass Brazil. We will continue with lecture 3 today on chip pulse shapes and multiplexing. So yesterday we have been talking about signal properties, the multiple access of GNSS signals, how this is organized to separate the different information coming from different satellites and also to perform ranging to different satellites. And we have seen that a lot of these properties that we discussed are related to the chip pulse shape in the end. Most of the properties of the signals are related also to the autocorrelation function of the signals and also to the cross correlation function between the satellites or the signals. So today, finally, we will discuss about the chip pulse shapes because they will form the autocorrelation function of the received signal. And we will use this autocorrelation function to estimate time delay, as we learned yesterday. And we will also use this, is also significant when we talk about the interference between the satellites and so on. So I will introduce very briefly and quite fast the chip pulse shapes that are in use today. Yesterday I showed you also some designs of chip pulse shapes that I did just to explain the properties. So there's also some work going on in the Galileo and GPS signal design where people look at designing chip pulse shapes for future signals. Today we will go through the ones that are used today for different by different systems. And then afterwards we also have a look at how different signals, because each satellite is transmitting usually on different carrier frequencies, different signals. So each service has its own signal. For example, the GPS military service has dedicated signals. Then there are signals for the open service, and then they have 3 different frequencies. The same thing can be noticed also for Galileo. So you have different services. There's a high accuracy service. We will have a talk during the week also about this. There's an open service. There's also the authorized service, so the PRS service. And they all have dedicated signals for their users. And then this means that for each carrier frequency, we have several signals that we're transmitting on one carrier, and that we need to design this carrier signal in some way. So we need to multiplex the signals onto each carrier, and we will talk about these techniques, how to do that, and what is used today. So yeah, so this is our outline for this morning. So we will start with the classical one, chip pulse shape. So we will look into rectangular chip shapes, then into binary offset carrier signals, composite Bach and time multiplex Bach signals. These are specific implementations of binary offset carrier signals used by Galileo and GPS. And also by, there's a specific one also used by Beidou. And then we switch to signal mapping and multiplexing methods. And we will look at 2 classical methods already, signal interplex and alternate Bach. And there's even more modern ones, but we will just introduce this idea with these classical ones. Yeah, so chip pulse shapes, the rectangular chip pulse shape can be described by this formulation here. So the P of the rectangle of T, and then we have here 2 Heaviside step functions. Here's the definition of the Heaviside step function, the unit step. And we can use this unit step function to define a rectangle pulse. That the rectangular chip pulse shape can be considered as, as I said, as the classical chip pulse shape, which originally was used for early spread spectrum signals. So when you open a book about spread spectrum signals, you can, they all use rectangular chip shapes, and we get what the final signal. So when we use this chip pulse shape for our spreading sequence, so for the pseudo-random sequence, we end up with a binary offset, with a binary phase shift keying signal. This is how this looks like. So the chip shape here is normalized here to 1. So it's 1 from minus 0.5 to 0.5 divided by the chip duration. And this is the complex, in the complex plane, the received baseband signal. It's a BPSK signal. So we have two states. The signal is switching in between, and the two states are on the real axis in our case. Yeah, the Fourier transform and the autocorrelation function of the rectangular chip shape can be calculated as we have seen yesterday. These are two important metrics and to be considered when we talk about performance, when we calculate interference, and when we try to estimate parameters. So first, we can notice that the Fourier transform is a sinc function. Here's the definition of the sinc function that we are using. And here below, we can calculate the autocorrelation function, which is a triangular in our case. So for the rectangular chip shape, and we can also see here for infinite bandwidth. So when B goes to infinity, we have a triangle of the autocorrelation function of this chip shape, and we have this power spectral density where we have the absolute value of a sinc function with fastly decreasing side lobes. Yeah, we can then, instead of the chip shape, the rectangular chip shape, which is used by GPS signals a lot. So the classical GPS signals on L1, L2, and L5 frequency, they all use rectangular chip shapes. The new open service of GPS, the L1C signal, they use the time multiplex box signals. Galileo signals they also use on E5A, E5B rectangular chip shapes, and then on the other frequencies they use binary offset carrier signals, and we will chip shapes, and we will see now how they look like. So the box signals became the standard of GNSS signals. Besides using rectangular chip pulse shapes, the chip pulse shapes are formed by the product of a rectangular pulse. So we can again use here the Heaviside functions to define the rectangular pulse, while here now NC is the chip rate, and the chip duration is 1 over NC times FR, while FR is a reference frequency. And in this case, the reference frequency is always 1.023 megahertz. Then we have NS, which is the subcarrier rate, because now we multiply this rectangular chip shape with a square, cosine square or sine square wave subcarrier, which can be given by this G of N of S here, and NS times FR is here included in the defining the subcarrier frequency. And this is then the subcarrier rate is NS, and the subcarrier frequency is NS times FR. We can then introduce the definition of, we can define here this BOC NS NC, which indicates BOC signals with sine subcarrier, and BOC cos NS SC. This indicates box signals with cosine subcarrier. We can use this writing. You can also find this writing in the literature a lot about GNSS signals. So on the next slide, we can now see how we can build our chip shape. So we have here, this is the example of a sine-phased chip shape. So, because we have here the writing BOC NSNC, we can also have here BOC cos NSNC, then it is a cosinus phasing subcarrier. And then we just multiply the two, and as the rectangular chip shape is time limited, everything outside of the duration of the chip duration is 0, and inside we have the multiplication of the subcarrier, the square wave subcarrier times the chip shape, but it's just 1 in during the chip duration. I just want to comment here that the BOC11 signal with sine square wave subcarrier is also known as the biphase Manchester pulse. This exists since the 50s. This is a pulse shape used for telephones, telephone transmission, because you have no spectral support of the signal around the DC, so you can filter out any strong DC interference, which was very common in telephone line communication. So it's a split, also called split spectrum signal, these box signals, and we will see this on the following slides. We also get a binary phase shift keying signal, because we have only a binary real signal here. The chip shape is real and usually binary, or is binary. And the box signals, they achieve this FD-CDMA approach that we discussed already about, and we have seen already yesterday in one of the slides where I showed you the PRS, Galileo PRS signal, the GPS encode signal, and the open service, because these chip shapes, they now introduce a split spectrum, they're a split spectrum signal, which means that you can distribute the power inside the band a little bit, and you can shape this distribution of the power of the signal inside the band. And with this, we can implement this FD, so the frequency division part of the FD-CDMA approach. And this is used, for example, to separate military services or public regulated service of Galileo from the open services, so that they are spectrally separated. As I explained yesterday, this has the target to reduce interference between the services, but also has the intent, or we also usually there's the intention, if you want to jam a military service or you want to jam the open service that is not used in a sort of crisis, and you want to still use the military service, then they need to be spectrally separated. Otherwise, you also jam your own military service, for example. And that's why also military services of different systems are spectrally separated, because usually you want to be capable of jamming the other system's military service without jamming your own military service. And this is the whole idea behind this FD-CDMA approach. We can also define now n as the number of half periods of the subcarrier within the duration of one chip. The higher n, so this number of half periods, the higher the Gabo bandwidth. And if you remember from yesterday, the Gabo bandwidth is directly linked to the accuracy that we can achieve in the estimation of the time delay of the signal. So what we can see here, that for higher n, if we have a higher subcarrier rate, then we have a higher n, and this means that more power will be pushed to the band edge, and that we have a lower Kramer-Auer bound that we can achieve. On the other hand, we discussed yesterday also, the side lobes of the autocorrelation function will increase, and we can see this now on the following slides. I will show you some examples of these box signals that are used. So, for example, we can start with the BOC11, the sine phase and cosine phase. You have here the sine phased one on the left-hand side and the cosine phased on the right-hand side in red. This is the chip pulse shape. So you see we have one period of the subcarrier inside the chip shape, inside the rectangular chip. And here we also have the cosine phased one. We can also have a look at the autocorrelation function of the two signals. You can notice we defined this yesterday, this kappa, which is the height of the side lobe between the main lobe. So this is here the highest side lobe here. It's 0.5 with respect to the peak, the main lobe here, which is at 1. We can see there's a slight difference here uh, of the autocorrelation function of the cosine phased one. First of all, the peak is narrower, is sharper, which means that the Kramer-Rao bound of the Bock cosine one will be lower than of the Bock one, the sine phased one. We have the and this also will mean that there's more power of the signal pushed to the band edge to higher frequencies. And we can see this right now in the power spectral density of these signals. So we see that the Bock cosine has a tendency of having more power at higher frequencies, and that's why the Kramer-Rao lower bound of this signal is lower. We can here clearly see the split spectrum character of the signals. If we now increase the subcarrier rate, so now we have two cycles of the binary subcarrier within the rectangular chip. Now we have two cycles here for the on the left hand side for the sine phased, again on the right hand side in red for the cosine phased. We can have a look at the autocorrelation function as we as I said before. The higher the subcarrier rate, and the higher this number of half periods per chip, we expect higher side lobes of the autocorrelation function. Now we have here 70% of the main lobe height, which is at 1. We can again see that at the peak of the autocorrelation function is sharper. The peak is sharper for the cosine phased signal than for the sine phased signal. And if we look at the power spectral density, we can clearly see this now, that the sine phased signal has more power between the two main lobes that are formed by the split spectrum signal. And the cosine phased signal has more power outside of these main lobes and less power between the two lobes. This property can already be used if for our FD-CDMA approach, because we can, if we want to introduce signals to the allocated band. We need to think about, okay, do we want to have more interference between the two lobes to other signals or outside of the main lobes? In general, you have already signals at the center, so at the carrier frequency. So you want to distribute maybe signals outside of the spectrum at the center from other services. So these Bock cosine waveforms are very popular to distribute the power more to the band edge. For example, in case of Galileo, we have the open service is a sine phased Bock, based on sine phased Bock signals, and the PRS is based on a cosine phased Bock signal, because you have less power in the center and you have more power outside of the main lobes due to further to the band edge of the satellite. And if we now further increase the subcarrier rate, so now we have a 4-1 Bock 4-1 and a Bock cos 4-1. So now we have 4 cycles of the sine phased or the square wave subcarrier inside the chip duration. Again, on the left we have the sine phased, and on the right hand side we have the cosine phased. If we look here now at the autocorrelation function, the side lobes get really high, close to 90%. We have also a lot of side peaks. Again, the Bock cos tends to be sharper. The main peak tends to be sharper. And if we look at the power spectral density, we can see much clearer now the two main lobes, and we can see that the sine phased Bock has more power between the main lobes, less power outside, and the cosine phased has less power inside here in red and more power outside of the main lobes. And this idea or this property is used again to implement spectral separation of authorized and non-authorized services, for example, in the band. Yeah, then we can also build variants of these box signals. First of all, let's have a look at composite box and then at time multiplex box. Composite box, here I give an example for two signals. A composite box is a signal is a signal that is composed of a linear combination of several box signals. And I give here an example for two box signals with a weighting coefficient. So we have the weighting of W from 0 to 1. This Xi here is a normalization coefficient that will normalize the power to 1 again in our case, because I'm discussing here always chip shapes that are normalized to 1. So it fits to our general signal model. We can see here the Fourier transform of the signal. So we have here, and we can also linearly combine with a plus or a minus these Bock signals. And we can see here the Fourier transform of this chip pulse shape and then the power spectral density of the chip pulse shape. Now here you see why we defined everything here with square roots, because then we can see the weighting in the power spectral density of the different box shapes. So you see it's a linear combination of the power spectral density of a box A1, AB and the box CD with the weighting coefficient, weighting the power between the two. And then we also have a cross, somehow a cross term based on the Fourier transforms and the conjugate Fourier transform of the AB and the CD chip shapes. And we have here the Xi again is a weighting coefficient to normalize the power of the signals. How to calculate this? Now how to calculate the autocorrelation function of this? This is just the Fourier transform of the power spectral density. So it's related. It's a Fourier transform of this given by the Wiener-Khinchin theorem. So we have here then the autocorrelation function of the Bock1 AB and the Bock CD signal, and then some kind of a cross correlation between the two given by the real part of the Fourier transform of Bock AB and the conjugate of Bock CD. The normalization factor is just normalizing the power here. We can write this either in frequency or time domain. So that we achieve again that also the composite box signal is normalized to 1 in frequency and time domain. Yeah, for example, this composite box approach is used for the open service of Galileo. We can have a look at this signal more in detail. So we have the open service of Galileo having a data component, which is the Bock plus, and a pilot component, Bock minus signal, following two Bock signals. They are so they're following now. They're built now two composite Bock signals, and we built the Bock plus one is a composite Bock of a Bock 1,1 and a Bock 6,1, and we also have the Bock minus, which is the pilot signal, is a Bock 1,1 minus a Bock 6,1. And we can see here, this is the weighting coefficient, 10 to the 11 and 1 to the 11th. And the overall PSD of the sum of both signals, so we take now the PSD of the Bock plus and the Bock minus, and considering that we have 50% of the power for the data component and 50% of the power on the pilot component, we get exactly this, that we have 10 11th Bock 1 power spectral density and 1 to the 11th Bock 6,1. And this is then the power spectral density of the Galileo open service. The cross terms, they disappear because we have used here a plus and here we have a minus. So this cross terms of the power spectral density of each CBOC signal for the data and pilot component, they disappear in the overall sum PSD of the open service, and we only remain with these two pulse shapes, with these two contributions of the Bock 1,1 and the Bock 6,1 in the power spectral density. Yeah, if we look at the chip shapes of these two signals, so the pilot, the data signal is given on the left, right? It's the, yes, the data signal is given on the left, and the pilot signal is given on the right. The difference between pilot and data is only that on the pilot signal we have no data, so we can integrate longer. We can more easily estimate the parameters, time delay, Doppler and phase of the signal. And on the signal, on the data signal, we then have the navigation message modulated. We can then use this signal only to demodulate the message. But we can also use all the signals for parameter estimation, because 50% of the power is also on the other signal, on the data signal. So there's a lot of ways how to process the two signals, either in combination or separately, processing only the pilot and using this the data signal only for the data reception. This also indicates now that maybe in the future there's more optimization done, let's say in the direction optimizing the data signal more for data transmission and optimizing the pilot more for parameter estimation. In this open service of Galileo, this is still not driven too far. Yeah? So we see a little bit, because when we look at the autocorrelation function, we can see that the pilot signal is a little bit better for the parameter estimation, but not that extreme. I think we could go more to an extreme case, designing a pilot signal really extremely designed for parameter estimation, for robust parameter estimation, and going for a data signal that can implement higher data rates and is maybe more optimized for data transmission. But this is Galileo already did a good job with this signal design. We can see here that the pilot has a little bit more higher frequencies. Here at the 6.1 component, there's a little bit more power, and that's why we will expect a lower Kramer-Rao lower bound, a sharper peak of the autocorrelation function, and we can already see that here in the autocorrelation function. The pilot has a little bit sharper peak, so we expect a little bit better parameter estimation. Still, we have nearly 50% of the side lobe height, but we still have a very nice formed autocorrelation function for our tracking algorithms and parameter estimation algorithms. So this is because that's the cost function that we have to evaluate to estimate the parameters. And we have some side lobes we have to take into account, these side extrema here, besides the global maximum, but they're not severely high. So they're around 48% of the main lobe, which is quite good. On the other hand, we can also use time multiplexed Box signals. Time multiplexed Box we use for time multiplex Box, we use different pulse shapes for different chips of the PR sequence. So not all the chips of the PR sequence use the same chip pulse shapes. We vary the shape. Okay, and a time multiplex Box signal with two different Box chip shapes, which are emitted each duration of the chip, can be given by this formulation. So we have Box AB with a probability of P, and we have Box CD with a probability of 1 of minus P. Yeah? And then if we assume that the signal is negative equally probable, which in principle means that we have for both of these chip shapes equally probable negative and positive phased chips, then the PSD of the time multiplex Box signal, where we add the time multiplex Box signal with these probabilities of these two pulse shapes, we get P times the power spectral density of the Box signal AB and minus 1 minus P of the Box signal of the Box CD signal. And also the autocorrelation functions are directly weighted of these two chip shapes. So it's nice. We can use this time multiplexing of chip shapes to form our autocorrelation function to optimize our autocorrelation function and also to form the spectrum. So also implementing the FD-CDMA that we discussed. Yeah, this approach is used by the Galileo L01C, so the new open service of GPS, I'm sorry. And this is transmitted on the L1 frequency band, besides the GPS CA code signal, which is the most used signal in your cell phones today. And for the L1C signal, we have again two components, a pilot and a data component. And they're defined as follows. So we have the pilot component. This is 29 to 33 box 11 and 4 to 33 box 61. And the data component is a pure box 11 signal. Is not a So we have only one chip shape for the data signal. And then the distribution of the power between the pilot and the data is different. Data. And then the overall PSD of the L1C signal Okay, we're back. Okay, so the sum PSD or the overall power spectral density of the L1C signal then can be given, considering this power sharing between pilot and data, is 3/4. Okay. Okay, so the overall PSD of the L1C signal is given here below with the power sharing of 3/4 of the pilot to 1/4 of the data. And we end up with 10 to the 11th of box 11 plus 1 to the 11th of box 61. And this is the same power spectral density of this overall open service signal with the two components then with Galileo, right? We just talked about this. So they end up with the same power spectral density of the complete signal, but they have total different implementation of the signal. This is because the power spectral density is only about the amplitude of the signal, right? So or the power distribution is the same, but we have different phase of the signal over time, and so we can have a different implementation, but we end up with the same power spectral density. So this was a quick summary of the used chip shapes today. So rectangular chip is used for the majority of signals still today. There are some signals that use BOC, binary offset carrier signals, chip shapes, especially then the new open service signals of Galileo and GPS, and also the military services of Galileo and GPS use also BOC signals in order to introduce mainly the FD-CDMA, increasing spectral separation between authorized and non-authorized services, and also of signals in general in the band. And as I said yesterday, as we are moving also from noise limited case for GNSS, because in the beginning Galileo, GPS, and GLONASS started in totally different bands. They were perfectly spectrally separated, and at that time, with only like 12 satellites being received at maximum at a certain location, you only had very limited intra-system interference and basically no inter-system interference. But with now Galileo Beidou all pressing into the same bands as GPS, and also GLONASS in its modernization also entering the L1 band, for example, we see that there's more signals being transmitted, more services provided by GNSS today in the same bands, and this spectral separation will become more important, I think, in the future to manage the interference between the systems. So, in my opinion, we are more moving towards an interference limited case now, because also all the systems are ramping up the power. So they're discussing in their modernizations and evolutions to increase the power on the satellite, on the payloads. So we are kind of moving towards this more interference limited case than only being noise limited in the receiver. However, as I mentioned also yesterday, there are methods to also be used in the receiver to combat this interference. We can use multi-user detection and mitigation in the receiver. As we're estimating all the parameters of all the received signals, we can use this to subtract this interference from the incoming signal, and thus also to mitigate the multiple access interference. But this is a work. There are a few papers already available discussing this for GNSS, but the majority of this work was done in many years ago for communication systems, which are definitely only interference limited. The noise is playing a minor role in communication systems where you have hundreds of users that are using the same frequency band. And for them, it's more the interference driving the performance. And there also have been methods already developed for communication systems. However, they have optimized these methods with respect to bit error rate and not with respect to parameter estimation. In our case, the bit error rate is, as I said yesterday, the transmission rates are very low. The data transmission demand is not really high. In our case, it's more important to perform synchronization and then ranging and parameter estimation. I think these methods these multi-user detection and mitigation methods, they maybe have to be adapted for our case and optimized for the parameter estimation case. But okay, there's already some papers suggesting methods also for GNSS, and I think in the future we will see them also being more considered in receiver designs. Yeah, now let's move on with how can we now interplex or multiplex or map, there are several words for that, several signals onto one carrier. As I mentioned before, we have several carriers for each satellite, and each satellite is transmitting several signals on each carrier, and these signals are allocated to different services. So the goal here is to map several signals onto one carrier frequency, achieve minimal crosstalk and maximal power and bandwidth efficiency on the payload. Especially we will talk about the high power amplifier. Each signal provides a different service. And in general, there are two main strategies. So there's time multiplexing and frequency multiplexing. We will not talk about time multiplexing here today, but there's also some methods where you can time multiplex several GNSS signals. There's an example of one of the GPS services. They use time multiplexing, but we will talk about the frequency multiplexing here, and we can achieve a constant envelope of a baseband signal S of t, which is the sum of all the waveforms Sn of t, and this power and this constant envelope can be defined by what's called the peak to average power ratio. The PAPR is given by the maximum of this waveform, the absolute square of the max of this waveform, divided by the expectation squared of this waveform, and this should be 1. Then we have a constant envelope signal in the complex domain, and this is preserving is usually very beneficial for the amplification of the signal on board the satellite with a high power amplifier, and this prevents also out of band emissions. Because the high power amplifier usually is a non-linear device, and when you there's a linear region usually of the amplifier, but when you leave the linear region, you can, and this depends where you define the operational point of the amplifier or the operational stage of the amplifier, and point. Then maybe parts of your signal will enter this nonlinear region, and this can create spectral regrowth, so out of band emissions, and also creates power inefficiencies, or this can also create this clipping, what's called clipping of the signal, and disturbance in the signal. Yeah, but we will focus here on methods that achieve a constant envelope signal. They consider also all binary waveforms. And this is maybe also one of the reasons why maybe until today only binary waveforms were chosen for chip pulse shapes. But it's not necessary that these methods, they can also be applied for signals that are not binary. Okay. A phase modulated radio frequency passband signal in a phase shift keyed phase modulated, so PSK-PM system, can be given by this formulation here. So we have the square root of 2p. P is again the total power, the average power. Then we have here a sine wave signal, where we have here the carrier frequency Fc. N is the number of channels that we have. Then in this phase term, we have several signals, so a superposition of several signals. So we have a phase shifted signal. You can see here we have a sum of a weighted sum, quasi a weighted sum of the signals with N2 up to N, and this is then multiplied with the signal 1. And this defines our phase term. Then we have the so-called modulation angles beta, which are the weighting coefficients here for the signals as beta n to Sn. And we also, as I stated, we assume that the binary data streams are binary GNSS signals. Now let's have a look at the case of a two-channel interplex. We start very simple here. So we can include here the phase term for the two-channel interplex. We have now S1, beta 1 times S1, and beta 2 times S1, S2 as the phase term of the signals. We can apply the following theorems here. The first ones are classical theorems from trigonometry, and then we can also assume here, as Sn is binary, beta n times Sn is equivalent to cosine of beta n, and because Sn is binary, you can also state that beta n times Sn, the sinus of this, is Sn times sinus of beta n. And we can, when we apply these theorems, we can reformulate this signal here S tilde, which is the passband signal, the passband multiplex signal. We can see now that we have a component here of a sine carrier with two components, and a multiplication with a cosine carrier and another two components. We can now further, if we calculate the power of these, which is then here the in phase and the quadrature component, we can now calculate the power of these four signal components. And we can see that we have a carrier power where we have the total power P times cosine square beta 1 cosine square beta 2. This is the power of the first component here, which is given. There's no signal, there's no information transmitted. This means that's why it's called carrier power. And then we have the two signals that transmit information, P1 and P2, and we have what's called the intermodulation product, which is So we have here the signal here P2, and we have here the signal 1, and we have here this intermodulation product, which is defined by the multiplication of the two signals. And this is then this power, the intermodulation power. When we choose now, what we can do now, first we can choose beta 1 equals to pi half, and then the carrier power disappears, becomes 0, which is good because it doesn't transmit any information, right? So we choose the angle now beta pi 2, and if we want to achieve now equal power between the signal 1 and 2, we can choose the modulation angle 2, so beta 2 to pi over 4. And we result in a very nice case now. The carrier power is 0. Also, the intermodulation part is 0, which is good. And then we have only power allocated to the two signals that are useful. This is a very well-known case. This is the quadrature binary shift keying modulation, which is used in many cases in practice. But you see that we can, by choosing this beta 2 in a different way, we can also create we can also create QPSK signals with non-equal power in P1 and P2. So if we look at the complex baseband signal, remember that we had S tilde is the carrier, is the RF carrier signal, so the passband signal, and we can also write this in the form of a baseband signal is a complex baseband signal. Then here you have the relation between the complex baseband signal and the passband signal. And here we can see then in the complex domain, in real part of S and imaginary part of S, we can see the constellation diagram of the signal. So we see that we have 4 states of the signal. They all lie on a circle, which is good because in principle this implements our constant envelope. Remember that we have assumed binary signals with infinite bandwidth of each signal, and then these transition lines that we have here, they're happening at no time. So in principle, the signal stays always on this circle, which, and the radius of the circle is defined by the 2 powers, but also the location of these points, they're defined by these 2, the power of signal 1, power of signal 2. So the states can be different for different power shares of the signal. Yeah, but what happens if the signals are not absolutely band limited and we still use this interplexing or multiplexing scheme? Then we have also transitions between these states that can also, so we can, over time, we could have some values of the signal. When the signal is passing from this state to this state, we have also values here inside this circle. And this happens when the signals before the amplifier are not absolutely binary. And when we generate the signal on board the satellite or at any transmitter, this is always the case. We generate a signal that is not binary absolutely, because we do that in a digital domain and so on. So the signals are usually have a certain bandwidth also before the amplifier, and that's why we have these transitions. If we want to avoid these transitions, there's a way of doing this. And these transitions, they depend on the absolute bandwidth of the signal. So if we want, but still, if we want to avoid these transitions, in case the signals are not absolutely binary or they're not binary, we can still, we can delay the signal 2 with respect to the signal 1 a little bit. And then we can avoid these transitions here from the state here in the first quadrant to the third one, and the transitions from the second to the fourth quadrant. we can avoid them. We have then only one signal component changing phasing at the time instant. So only these transitions in red are possible for this delayed one, which is called also staggering in the literature. And this is then here the special case of what's called offset QPSK. So we have a QPSK modulation with an offset. If we use the same chip shape on both signal components, then this delay is exactly half a chip. We can also play with this delay dependent on the chip shape. We can achieve also better PAPR if we play a little bit with these delay. So then the optimum delay, maybe if we don't use the same chip shape for both signals, if they're binary maybe or are band limited and this becomes non-binary anymore, then we can also find an optimum staggering value. So an optimum delay value to reduce these transitions in the center. And if we reduce the transitions in the center, we automatically reduce our peak to average power ratio also. Yeah, if we now move on to 3 signals, so we can have a look now at a 3-signal interplex of binary signals, then we can see here the phase term is expanded further with a 3rd signal. So we have the signal 1, product of 1 and 2, and 1 of 3. And then if we look at the bandpass signal, we have now here 3 components inside a cosine in the in-phase part, and in the quadrature part we have also 3 components inside a sinus. Then we apply all these theorems that I introduced a little bit before, and then we can get for the A1 part, so for the in-phase part we can get 1, 2, 3, 4 terms, and for the quadrature part we can also get 4 terms. And when we choose already beta 1 again equal to pi over 2, we end up with 3 useful signals plus an intermodulation product, and all the other terms they become 0 because of this choice of this modulation angle. This is already good because we're only wasting energy or power in this intermodulation product now. And all the other power is distributed to the useful signals that transmit information. We can now have a look at the constellation diagram. How does this look like for a 3-signal interplex? So this is again the complex baseband signal that we can have a look here in the complex domain, with here having on the x-axis we have the imaginary part, and on the real axis, on the y-axis we have the real part. And we can see here in black. In black, this would be the superposition of the 3 signals without the intermodulation product. So this would be just having one component in phase and the sum, a weighted sum of the two remaining signals in the quadrature component. And we can see this here, that we get this quadrant with these states, but not all this or none of the states are on the unit or on the circle. This means we have no constant envelope signal. But if we introduce the intermodulation product, these states, they move from the black ones to the brown ones. So the intermodulation product introduces this shift of the states to the circle, which means if the signals are only operating on the circle, we have that the maximum, the peak to average power ratio is 1. Because the maximum of the signal power or the signal absolute value is then equivalent to the average value of the absolute valued square of the signal. So we can see that the intermodulation product kind of introduces a pre-distortion or introduces a distortion of the superposition of the signals such that the constant envelope can be realized. This is important only before the amplifier on the satellite. So the signal can then be amplified very efficiently by the amplifier if we are having a constant envelope, because the amplifier can be operated close to saturation. And thus has the highest efficiency, and we have no spectral regrowth and so forth if the signals are exactly binary. Now, if the signals are not binary, in reality this is the case when they are generated, then we have to maybe introduce a little bit of back off in the amplifier, but still we can be operating our amplifier very efficiently due to the introduction of the intermodulation product. However, this costs power. So some of the power that could be used for the useful signal is directed now to the intermodulation product, and to ensure this constant envelope. And we could think about optimizing this, saying, yeah, what if we tolerate some clipping of the signal, we can tolerate maybe some distortion of the signal, and not wasting this power. And this is something that is also discussed in the literature right now for GNSS, looking at the distortion level of the signals, reducing the power used for the intermodulation product. There's also other methods that try to optimize the interplexing adaptively by optimization processes. So there's a lot going on to transmit the signals more efficiently. And we will not discuss this here, but in the literature you can find a lot of literature, or you can find a lot of papers on optimizing interplexing also and multiplexing. Yeah, if we, for example, look at the three signal interplex case now, and this is the case that we can, for example, how can we design now these intermodulation angles? So we can say that, for example, the signal 1 has twice the power as signal 2, and signal 2 has the same power as signal 3. And with this, we can then use these equations from our power derivation to identify the beta 1 and beta 3, for example, beta 2 and beta 3. As you may remember, the beta 1 was already selected pi over 2, and when we now have selected these properties for our power distribution, so the first signal has double the power as the second, then the second and the third, and the second and the third, they have equal power. We can now calculate how much power is distributed to each of the signals. So signal 1 has 4/9 of the power. The signals 2 and 3, each one of them has 2/9. So double the signal 1 has double the power than the signal 2 and 3. But we also have to spend 1/9 of the total power of the signal for the intermodulation product. Okay. In general, if we have one signal that's very strong and we have a lot of signals that are very weak, this this intermodulation power that we have to, this power that we have to spend on the intermodulation product gets smaller and smaller. However, if we, for example, have 3 signals with the exact same power, the intermodulation power we have to spend a lot of power in the intermodulation product. So this interplexing method is more efficient if we have the case that there's one strong signal and a lot of signals that have much less power. Yeah, and then finally I want to discuss the alternate Bock interplexing, because it's implemented on the Galileo E5 carrier, which is equivalent to the GPS L5 carrier, or close to the L5 carrier. The E5A signal of the E5 carrier is equivalent to the L5 carrier. And let's have a look into this. So now the task is to interplex or multiplex 4 signals And we want to also create minimum intermodulation products. So first of all, we could look into what is constant envelope output. Um, and I just want to explain this, how this is realized. We have then a sum here. You can see this is the complex baseband signal, equivalent signal. And then we have S1 plus JS2, and we have here a signal psi prime M, S3 plus S4, JS4, psi prime psi M. And we have then these S1 bar and S2 bar, and we have a psi pi bar M. And we have also these signals S3 bar, S4 bar, and psi bar M. These signals S1 bar to S4 bar, they are intermodulation terms. So in principle, we have two QPSK carriers, QPSK signals, modulated with multi-level subcarriers. Plus, we have another two QPSK signals multiplied with multi-level subcarriers, and they are all superpositioned. And we achieve here then these multi-level subcarriers are defined like this. So we have psi plus j psi t minus 1 over fs. And the psi bar m is the sum of the psi bar t plus j psi bar t and so on. And I think on the next slide I will define psi, hopefully. Yes, and these are the two multi-level subcarriers, the basic ones. And before, it's a little bit confusing. We have here superpositions of these basic subcarriers. Here it's a superposition of psi and a shifted version of psi, and also here for the psi m prime, it's a psi and then minus. So that's why it's called m, because it's minus a shifted version of psi. And for the bar versions are using also shifted a sum of shifted versions of psi bar, and so with a plus, and the psi bar m prime is using here a minus in the superposition. So this is how to understand this. We have then here a multi-level subcarrier, psi and psi bar, and they're looking like this in time domain. So we have here the psi bar. You see, they are not binary anymore. They have multiple levels. And also the psi signal in black has multiple levels. And this achieves then a constant envelope with 8 states, looking like an 8 PSK in the end. And we have a power spectral density that can be achieved with this multiplexing. In general, we are multiplexing 4 different signals on one carrier frequency in the middle, but we have also achieved to transmit 2 QPSK signals on 2 different subcarriers. Yeah. And this is very interesting. We can also see here in green and blue, we can see the power spectral density of all these intermodulation products. And this is a specific example for that this subcarrier frequency is 15 times 1.023 megahertz. And we have a chipping rate of all these signals of 10 times 0.3 megachips per second. And this is the case of Galileo outbox signal. The interesting case is we can use the complete signal in the receiver to process for processing as a model, and then for correlation we can build this complete signal out of the 8 components and use this for correlation, which is then called outbox processing. But we can also we can also use in the receiver, for example, tune our carrier frequency maybe to the E5A subcarrier, so only receiving then the red one, the red power spectral density, and maybe also filter in the receiver. And then we only receive the E5A pilot and data, which are in phase and quadrature. And there it's a classical QPSK modulation then. The same thing we can also do for the E5B if we want this. We can tune our carrier frequency in the receiver to the E5B subcarrier and only receive the two signals of them. We can also use there's also ideas about using other combinations of these two signals. And if you look at the spectral analysis, maybe in some papers of measurements of the spectrum coming from the signal, you will notice that these side lobes here of the intermodulation products, they are sometimes not visible or even or very, very much degraded. This is because after the amplifier on the payload on the satellite, they have also an output filter after the amplifier. So I just want to stress again, these interplexing methods, either interplex or outbox or other methods, they're only important up to the amplifier. Yeah, this is the whole reason is why thinking about this problem at all is to optimize the amplification of the amplifier for a superposition of signals, a mapping of signals. Yeah. After the amplifier, it's not important anymore, for example, to have these intermodulation products and so on. So in many cases, some of the satellites, they cut the filter, the output filter already cuts part of the intermodulation products and so on. So you will not receive them in the receiver at all. That's why the power spectral density can look a little bit different, but we are considering here, this is the power spectral density then before the amplifier and before this output filter. Yeah, this is my last slides for the introduction to chip shapes and multiplexing. And now we still have some time for questions. You had some questions.
Go back, please. Some slides there.
Yes.
The black dots, it's without any
without the intermodulation product, we end up with the black dots.
And without the intermodulation, the transition would be a square shape?
Yes, it is then a square shape here, as you can see. So none of these states that are organized by a square, and these levels are dependent on the powers of P1, P2, and P3. But none of these states will be on the circle.
And when we add the intermodulation, we then transmit no information, right?
We don't lose information. We add another signal that is built from the other signals. So we add a new signal that is a multiplication of all the other signals, and we don't lose information because all these signals in the receiver, they're separated by correlation.
Okay.
So we only have maybe a small cross correlation between the component 1, 2, 3, and maybe also the intermodulation product, but it's very, very small. And as I said, a lot of times the intermodulation is even filtered out by the output filter, so the satellite is not even transmitting most of the part of the intermodulation product. But in general, we are not losing any information here.
Okay. Thank you.
On the other hand, if you would demodulate, I mean, you could in the receiver also use, and this is also for the interplex, you could use a replica building exactly this signal, and then you can demodulate the complete signal. In many cases, this is not possible for the user because one of the components is a cryptographic signal. So in many cases, for the non-military user, this is not possible to demodulate the complete signal on the carrier. So that's why they stick to, okay, we only correlate with one component or two components in the receiver.
Okay, thank you.
Do we have questions from the chat? Do we have more questions in the room? Okay, then thank you very much for your attention. We now go to the coffee break a little bit earlier, I guess. When do we continue? At 11 o'clock, right? Yes, so the next talk will start at 11 o'clock Brazilian time, and this is 4 o'clock Central European time. Yeah, with the second external talk. So see you then at 11 o'clock Brazilian time or 4 o'clock in the afternoon Central European time or wherever you are.